All right. What's up? 2 minutes. Mm-hmm. Yeah, the parking lot was pretty empty today. So I'm assuming there's gonna be people that don't show. Then again, most people show up right at 12:30 for this class. So there is that. All right. 12:30. We're going to get started. Lord, thank you for bringing us together this afternoon. Thank you for the couple days off that we're going to get. Pray that you would help us use that time to get some things done, but also get some relaxation to recharge ourselves and prepare ourselves for the final 3 weeks of the semester. In your name we pray. Amen. Okay. First things first, nobody sent me any CLC team things. So I didn't see anything come in through private message or anything. I didn't see it. I'll double check when I get back. But if you haven't sent out who your team is, remember teams of 3, please do so immediately, right? Immediately. When you get back from break, I'm going to hand out the rods for all the teams, right? And you guys can actually you guys can take them now if you want them. Right? They're up here. I'll hand them out at the end of the class once people figure that out. Okay. Okay. Nothing on there. So last class we talked about work energy, right? So, yeah. All right. When I get back to my office, I'll take a look and see what's going on. It might just be hidden for some reason. So I'll double check when I get home. Yeah, for whatever reason, I'm not getting private forums right now. I'll go in and I'll double check and make sure, right? All right, guys, come on. Take a seat. Class has already started. Yeah. All right, cool. If you haven't sent me your CLC group, tell me your CLC groups, like ASAP. Okay. All right, homework 6, learn smart, do this weekend. And then really, we've got, outside of that, we've got the CLCs, remember, groups of 3. And the last exam, right? 2, there's one more exam that will cover this topic and the next one, right? So work energy, impulse momentum, and gyroscopic motion. Right? All right, so as a way of recapping, since there's nothing on the thing, all right, here we go. That problem we did in class, right, with the bar. If we wanted to find the reaction forces at B, how would we do it? All right, so you've got 3 choices, right? You want to find the reaction forces at B. You can either A, apply linear momentum to solve for bx delta t and by delta t. You can use work and energy to determine the work done by the moment at C. I can't see C in there. Now you can see C. Or you can use the sum of forces and sum of moments equation when the bar is horizontal. So, all right, show of hands, who thinks that it's A? All right, who thinks that it's B? And who thinks C? It is in fact C, right? Just like we did another problem last class, right? Before we did this one, where we wanted to find the reactions at the pin, right? Whenever you're looking for reaction forces, you want to use Newton's law. Now that changes if you're told how much time elapses, right? If you're given delta t, then you certainly could use linear momentum, but we weren't in this situation. We weren't. So
I just wanted to double check.
That's what Nathan asked at the beginning of class. I'm going to check when I get back to my office and make sure it's there. I probably either one of two things happened. It either got hidden or I forgot to actually assign it. Either way, that'll be rectified at the end of class. All right. So we're going to switch gears. We're going to stop talking about work energy. We're going to start talking about impulse and momentum, and what comes with that is also impacts, right? So we've got impulse, momentum, and then towards the end of class, we'll get into impacts, right? So we've talked about impulse and momentum before. We talked about it for particles, right? And we did talk about angular momentum, but we didn't do a whole lot with it, right? We did more of it with systems of particles, right? But when two rigid bodies collide, we can use the principle of angular impulse momentum. We often use linear impulse momentum like we did for particles, right? So again, right, momentum is this vector quantity, right? So we need the x components and the y components. And just like Newton's law, we've got some of the forces x, some of the forces y, and some of my moments, right? Well, in this case, we've got some of my momentum in the x direction, my momentum in the y direction, and the sum of my angular momentum, okay? So it's equivalent in some ways. All right, so here's this slide again. We've seen it a couple times, right? But how do we know which type of problem we're supposed to be doing, right? Well, ask for forces and accelerations, use Newton's law. If you're asked for velocities and displacements, use work energy. And what we're going to be focusing on today is if you're told velocities and time, then you want to be using impulse momentum. In fact, anytime for these problems that we're about to see that you are told how much time has elapsed, you should always be thinking impulse and momentum, because this is the only equation, right? These two are the only equations that have time in them, right? The only ones. Let's watch a video.
In football, running backs specialize in being elusive, agile, and fast in order to gain the maximal amount of yards per play. They do this by spinning, juking, hurdling, or hitting defenders in order to keep forward motion. But elite defenders do just the opposite by stopping the running back at all costs.
Hi, I'm Matt, and on this episode of Sports Science, my fellow exercise scientists and I are going to take a look at who wins collisions between running backs and linebackers. We're going to do this by investigating the concept of linear momentum and how it applies to the gridiron. So first, we'll start out by talking a little bit about the concept of linear momentum. What is it?
Linear momentum is described as a product of mass and velocity. Therefore, any object with mass, which is anything in existence in the universe, that is moving at however fast, has momentum. Now, when two objects with momentum collide, they combine together to have a new total mass, and will continue moving in the direction of the object that had the larger momentum at impact. Thus, the winner of a collision is determined by whatever object can produce larger momentum and continue movement in the starting direction. In our case, we have a couple of meatheads that will be producing maximal bromentum, a running back and a linebacker. Both will be exactly 4.6 meters away from the line of scrimmage and will accelerate towards each other to create a brolism, with only one victorious bro. The bro 1, our running back, will try to cross the line of scrimmage, while bro 2, our linebacker, will try to prevent the running back from crossing. The winner will be determined by whoever has the greater momentum when they slap carcasses at the moment of collision. Now, let's meet our colliding bros. This is Ryan, our linebacker. Ryan can run the 37-meter dash in 7.4 seconds, making his peak velocity 5 meters per second. But his mass is an unbelievable 1,600 kilograms. That means he packs as much meat as your average giraffe. This is Brad, our running back. Brad's mass is only 500 kilograms, but he can run the 37-meter dash in just 4.3 seconds. That's lightning fast. So who wins? The lightning fast running back or the massive linebacker? To answer this question, we packed up our science hardware and headed out to the Sacramento State testing field with our exercise scientists to run this experiment. Our first trial consisted of both players lining up 4.6 meters away and running full speed when prompted. Let's see who wins. Ryan wins by a huge margin, but why? At this point, just before collision, Brad has a linear momentum of only 4,300 kilogram meters per second, while Ryan is at 8,000 kilogram meters per second, meaning the two of them will assume a new combined momentum of 3,700 kilogram meters per second in Ryan's direction. For our second trial, we decided to take a shot at evening the playing field out by adding 250 kilograms to Brad's mass, giving him a new mass of 750 kilograms. Let's see if that's enough to observe a change in his momentum and return the favor to Ryan. Ouch! Looks like Brad comes up short once more. Despite his ability to generate a momentum of 6,450 kilogram meters per second from his newly added mass. But what if we add 250 more kilograms to Brad's mass, making his new total mass 1,000 kilograms, and keep his speed constant at 8.6 meters per second? Whoa! Brad was able to generate a momentum of 8,700 kilogram meters per second, which beats Ryan by 700 kilogram meters per second, and continues movement in Brad's favor to get past the line of scrimmage.
What did we learn today? We learned that the winner of a collision is the one who carries the more momentum before colliding. Whether that means they have more mass or more velocity, whichever combination of those two variables being the highest is going to have a net velocity in their direction. So, we saw examples of that when we put weight on Brad, and we saw that he still didn't have enough mass times velocity to move Ryan, but we added more weight and he was able to win the next collision. Thanks again for watching. Again, I'm Matt, and this has been Sports Science. All right, boys, let's get ready to hit the showers.
Okay, so clearly not really ESPN Sports Science. Yeah. Yes. So, right, and I heard Zach saying, right, wouldn't he just be slowing down the more mass? You can't assume that the velocity stays the same, right? And that's true. But the point is that if two things are going to collide, right, the one that has the more momentum is going to dominate that collision, and that is what is going to determine what direction two things that hit each other end up going in, right? Now, it's a little bit different on the playing field, right? But the general idea is sound, right? So the method of impulse and momentum is well suited for the solution of problems that involve time and velocity, and it is the only one that we will use for collisions. Okay, and we talked about how we handle collisions of particles, and we handle collisions of rigid bodies very similarly, right? So for example, right, if we have our potato back again, I've got, my sum of my momentum at the start, plus all of the external impulses that are applied to my object. Right, remember, an impulse is what? Well, it's just the force times the change in time. Right, because what is an impulse? An impulse is a large amount of force that happens over a very short time. Right, think of a nail being hit by a hammer. That's what we're talking about when we're talking about impulses, right? And so we're talking about all of these forces being applied over typically a very short period of time. And then that results in the sum of the system's momentum final, right? So initial momentum plus the sum of my impulses is equal to my final momentum, or the sum of my final momentum. All right. We'll talk more about momentum impulse diagrams in a minute and how we can draw these, right? Turns out that the momenta of particles, right? Momenta is just the plural of momentum, right? The momenta of particles of a system may be reduced to a vector attached to the center of mass, right? So if you were to sum up the momentum of every single particle in a rigid body, you could then take all of those and put it at the center of mass, right? So this is, remember, this is the same way that we handled systems of particles, right? And the way that we handle things when we're doing Newton's law, we are summing forces at the center of gravity, right? We're summing the acceleration of the center of gravity. We want to know how everything here moves, so we're going to track point G, right? We're going to track the center of gravity of this rigid body, right? So it helps us to be able to figure out this is the momentum vector for the center of gravity. And if you know that, you can break it into X and Y components, right? And we can also talk about all of the angular momentum that's generated by these three momentum vectors as well. Right, so a couple equal to the sum of their moments about the center of mass. So remember, the book uses L for linear momentum, pretty easy to remember, but H for angular momentum, right? And just like when we have moments, right, this is H sub G, meaning that it is the angular momentum about point G, okay? About point G. And what is that? Well, that's technically the sum of R sub I cross V sub I times delta M. Well, V sub I times delta M is just my linear momentum. So it's the sum of all of my linear momentum vectors and the distance vector that I am away from the point that I'm interested in summing my momentum about. Okay. For planar motions of a rigid slab or of a rigid body that is symmetrical with respect to the reference plane, H sub D equal I omega. All right, so remember, a few weeks ago, we talked about this. We said that in this class, we're going to focus on things that are symmetric, right? So symmetrical bodies. And because of that, we can say that the angular momentum is equal to I omega, right? Because we're talking about 2D problems for all of these things. We're not talking about 3D momentum problems. We're talking about 2D problems. What is I omega? I is the mass moment of inertia. Where do we get it? Get it from tables, or we can use our K value, right? Because I is equal to K squared M. Or we can create it, but for the most part, you'll either be given it, or you'll be given a table, or you'll be given the radius of gyration, and you'll have to calculate it. Times omega, which is the angular velocity. Okay. So let's draw our impulse momentum diagram, right? It's similar to a free body diagram. Where in the first step is we are going to isolate the body of interest, right? So I have my slab, and I've disconnected it from anything else. And in its initial position, right, the first part of this diagram, I am drawing the sum of my momentum. I'm doing the sum of all of my momentum, right? So I'm drawing all of the initial momentum that this object has. And it's got some linear momentum as defined by mv, and it's got some angular momentum as defined by I omega. We add to that the second part of this diagram, right? And the second part of this diagram is the sum of all of my impulses. So I draw my forces, right? I'm going to draw my forces on there. Where are they acting? You know, what's the angle of these forces? And I set all of this equal to the momentum at the second stage. So my angular momentum and my linear momentum. Now, this is the same thing that we did for particles, right? And this in a 2D problem will lead to 3 equations, right? Because you'll have the sum of the linear momentum in the x direction, the sum of the linear momentum in the y direction, and the sum of your angular momentum about some point, typically the center of gravity g. Okay, so let's walk through this. All right, so a sphere S hits a stationary bar AB and sticks to it, right? So you're at the carnival, you're gonna throw the ball at the target and the target's gotta go up, except that it's a crooked carnival and they don't want you to win, right? Because then they'd be losing money by giving out prizes, obviously. So you throw the ball and it just sticks. It hits here and it just sticks right to the bar, right? Great. We want to draw the impulse momentum diagram for the ball and the bar separately, where time 1 is immediately before impact and time 2 is immediately after impact. So we're going to draw the impulse momentum diagram just for the ball right before impact and just for the bar right before impact. And then we're going to draw it, well, so state 1, right, is right before impact, so just as it looks here. And state 2 is right after they've hit. So how do we do that, right? So what's the momentum of the ball before impact, right? Well, we're given the velocity, and it's in that direction. So the momentum of our ball before impact has to be to the right, right? Because our momentum is just the scaling of our velocity vector times the mass by the mass of the object. Mass is a scalar, remember? You either have mass or you don't. You don't have negative mass. Although, if you had a way of creating negative mass, you'd be rich, right? Because it'd be awesome. It'd be awesome for gyms. All right. Then we talk about the impulses, right? So right before impact, right? So let's talk about this, right? We're talking about the first state being before impact. I have to add to that the impulses on the ball as it impacts the rod, because the final state is just when it went right after it hits, right? So there is some impulse from the ball touching the bar, right? Think of it like the normal force, right? These two things are in contact, there's some contact force there, right? And then afterwards, the ball is gonna have some new momentum, mv prime, okay? Right, because it's going to have hit the stick and something's going to happen. And the stick was at rest to start. What about the bar? Before impact, there's nothing, right? The bar itself is just hanging there. It's not moving. There's no velocities. It's nothing. What about the impulses? Well, in this case, I've got the impulse from the ball hitting the bar. But I also have my reaction forces, right? So any force, whether it is an applied force or a reaction force, has to be taken into account when we are drawing these diagrams. And then finally, we get the final momentum of the system, right? It hits, ball hits the bar should start to rotate, right? So you'll have some I omega prime and some m rod, v prime rod, right? And assuming we have enough information, right, we can solve some things, right? Because we get 3 equations out of this. So we need to have no more than 3 unknowns if we want to solve 3 equations. So that's an impulse momentum diagram, right? And these are important, and you're going to want to have one. Because if you draw this out correctly, then writing your equation is essentially looking at the diagram, right? We'll talk about that again in a minute. What happens if I have a fixed axis of rotation that's not the center of gravity? So once again, right, I jam my rod through point O, and I'm going to rotate about point O. The angular momentum about O, I-O omega, is equal to I omega plus mv times r, but v is just r times omega, so hey, look, it's I plus mr squared omega, okay? That's also known as the parallel axis theorem. And that's important because there are lots of systems that we talk about that don't necessarily rotate about the center of gravity, the number one being the door. Right? The door doesn't rotate about the center of gravity, it rotates about the hinge. And so when we do calculations about a door, we need to use this as our I sub O, right? I sub O is just saying, remember that I bar is if we were measuring everything at the center of gravity. I sub O is saying I've now shifted this to point O, so I need to account for how the mass is distributed from there. If you equate your moments, your momenta, and impulses about point O, you get this equation, I omega 1. Right, so this is the angular momentum impulse equation, right? So the linear momentum and impulse equation says my linear momentum at state 1 plus the sum of my forces times delta t is equal to my linear momentum at state 2. The angular momentum equation says the angular momentum at state 1 plus the sum of my moments times delta t is equal to my angular momentum final. That's what it says. Why would we want to move this, right? Can't we just do all of our calculations from G? Sure, you could, right? But the nice thing about moving everything to O is that you have reaction forces at O. And so now they've canceled, right? And so you don't have to worry about them anymore. Nope. Just like we talked about with work and energy, you can separate every part of a system and apply impulse momentum to it. Okay? Or you can look at it as a whole. If you have more than 3 unknowns, it might be a good idea to split it apart and look at how everything's interacting. That'll buy you a few extra equations, right? This is every time you split it up, you get 3 equations for each body that you've split it up into. For each moving part of a system, the diagrams of the momenta should include the momentum vector and or a momentum couple. And internal forces occur in equal and opposite pairs and generate impulses that cancel out. We talked about that too, right? When we had 2 cars that hit each other, these 2 impulses of the cars hitting each other cancel, right? Because they're the same on each other. So from the previous problem, we saw that the impulse is acting on the sphere that is equal and opposite to the impulse acting on the bar, right? We saw that. So when the 2 things hit, they both exert a force on each other that's equal and opposite, right? They're in contact. So that's what happens. So we can take advantage of this and draw the impulse momentum diagram for the entire system. Right, so here, right, this is just our original one, right? The one that we just drew on the last page. We've got these things. And we've got this. And these impulses are equal but opposite, right? So they'll cancel. But if we wanted to draw this for the entire system, what would that look like, right? Right, so what is this? If you added these 2 things together, what would you get? So let me ask you guys this. Look just at this left column, right? First column, sum of my momentum. How much momentum do I have at the beginning in the entire system? If you were going to draw this, how would you draw the initial momentum for this system? How would we draw the initial momentum of the system of the ball and the bar together? How much momentum exists in this first state? What's that name? Zero for the bar. What about the ball? All right, so you get the top one. So what we're doing is we're taking the top one and we're adding it to the bottom, right? And if we do that, we'll just get the ball plus the stationary block, right? And we have everything measured to point A, right? Because we need these dimensions. Well, what about the second one? What does that look like? If you were to add these two things, so literally, right, I had MSVS plus MRVR and some angular momentum, right? I just added those two pictures together. If you add these two pictures together, what do you get? Think about what the vectors are here. What do I get, right, if I add negative F impulse delta T to positive F impulse delta T? What do I get if I add those together? Zero. There's nothing else here, so it just becomes the ball touching the bar with a reaction at A times delta T. What about the last one? What does the final state look like based on what we've drawn already? Remember, this is right after collision. So what would this look like? Compared to the first one, how does it change? How does it change? What should it look like in the final position? How would you account for all of the momentum in the system in the final position? How much momentum is left with the ball at the end? How much momentum is left with the ball at the end? It's not zero. Does it say zero in the figure? Does it stop moving? literally says in there MSV prime S. Well, it's hard to see because you're far away, but it has some final momentum, right? We talked about it a few slides ago. It said the bar hits the ball hits the bar, and it's going to go through the bar, right? It's going to cause the bar to move. So how much momentum is left with the ball? It's ms times v prime of s. How much momentum is left with the bar? How much momentum is left with the bar? Yeah, mrvr prime, and what else? Yeah, I omega bar, or I bar omega prime, right? So if we drew it, we would just combine these two drawings together. When we have these things split, the only thing that changes is we get rid of the impulses, right? We get rid of these equal and opposite impulses. This is a big idea because it's going to allow us to do a lot of stuff. Right? It's going to allow us to do a lot of different analysis. Right? Drawing an impulse momentum diagram is vastly important, right? It's super important. Right? It's like drawing a free body diagram. You absolutely 100% need it. If it's not on your exam, you're gonna lose points, right? So make sure that you draw it. We'll get lots of practice though, so don't worry. What about conservation of angular momentum, right? So here's my angular momentum equation right in the middle, right? So I've got I sub g omega 1 plus the sum of my moments dt equals I sub g omega 2, okay? And the only way that momentum is conserved, right, where I have the same momentum initial as I have final, is if the sum of my impulses is 0, right? If this term goes away, then I'm left with Ig omega 1 is equal to Ig omega 2, which would mean momentum is conserved, right? And this is the reason why figure skaters, right, we consider the momentum impulses to be 0, and as they bring their body in, they'll spin faster, right? Because why? Because they're not changing omega, right? Although that is the byproduct, but they're changing I sub g, right? They're changing the distribution of their mass. And so by bringing it in closer to center, it's going to cause them to spin faster, right? Because your momentum's conserved, right? If this is equal to 10, and originally I sub g was 1, but you've changed it to half, right? Now you've doubled how much omega you're going to have, right? When no external forces act on a rigid body, or a system of rigid bodies, the system of momenta at T1 are equivalent to the system at T2. All right. So if you don't have any external forces, then you have conservation of momentum. This is a fancy way of saying that. If there are no external forces, then you have conservation of momentum because there are no impulses. If the total amount of impulses end up canceling out, right, then you also have conservation of momentum, right? There are some things that throw a wrench into this, though. All right, when the sum of angular impulses pass through point O, the linear momentum may not be conserved, but the angular momentum about point O is conserved. So just because angular momentum is conserved does not mean that linear momentum is conserved. However, if linear momentum is conserved, it's a pretty good bet that angular momentum is conserved, right? It doesn't go both ways, though. Just because H is conserved does not mean that L is conserved. Two additional equations can be written by summing the x and y components of your momenta and may be used to determine two unknown linear impulses, such as the impulses of reaction. So we can use impulse and momentum to get reaction forces, but we have to be given some information, right? We need to be given the time or given the way to find how much time has elapsed. So let me ask you guys some questions. We're back to the bar and ball problem, right? For this problem, is angular momentum conserved about point G, right? So the question is about point G. Remember, sum of my angular momentum of G at state 1 plus the sum of my impulses about G has to equal hg2. And the only way that this is conserved is if the sum of my moments about point G is 0. Is the sum of my moments, so this is a fancy way of asking you the question, are the sum of the moments about point G equal to 0? So if you look at this central thing, do you have any moment about that central, about the center of gravity? Do we have any moments there? Any torques? Remember, a moment is a force times the perpendicular distance it is away from a point, right? So do we have any moments about point G that we need to worry about, or is momentum conserved? All right. So who thinks yes, momentum is conserved about point G? Show of hands. Who thinks it's no? You guys got to answer. It's 50-50. One more time. Who thinks it's yes? All right. Who thinks it's no? All right. It's no. Why is it no? It's not conserved. This reaction force, A sub x, is going to cause a moment about the center of gravity, right? A sub x is some perpendicular distance away. A sub y passes through G, right? A sub y passes through G. So what if I shifted it and I looked at angular momentum about point A? Would I conserve angular momentum about point A? Right, so this is asking what? If we change our equation now, right? Do we have any moments about point A? Right, that's what it's asking. So. Who thinks yes, angular momentum is conserved at point A? Remember, if the sum of the moments is 0, then momentum is conserved, right? That's what it is. It's telling you. So, who thinks yes at point A it's conserved? And who thinks B, or I guess no, it's not. Who thinks no? It is conserved here, right? Because if I sum my moment at point A, all of my forces run through point A, so there are no moments, right? So that middle term goes to 0. What about the linear momentum? Is linear momentum conserved in this system? Is linear momentum conserved in this system, right? So again, right, let's look at the equation and see what that has to tell us. Sum of my linear momentum at the start plus the sum of my forces delta t is equal to the sum of my final linear momentum. So is, right, we can break this down into x and y components, right? So what they're asking is the sum of the forces equal to 0? So for this problem, Who thinks linear momentum is conserved? Who thinks it's not conserved? It's not. Because the sum of my forces in the x direction is ax delta t. It's not 0. And the sum of the forces in the y direction is ay delta t. It's not 0. Because those reaction forces are there, we have to take them into account, and they go into our, right? And this is why the impulse momentum diagram is really important, right? Because it's a combination, right? It's kind of a combination of our energy diagrams and our free body diagrams, right? It's like we took the two things and we put them together. So let's illustrate this through a couple of problems now, right? And we did this one last class, but we did it with work energy, right? And so setup is the same. The system is at rest when a moment of 6 Newton meters is applied to gear B. If we neglect friction, we want to determine the time required for gear B to reach an angular velocity of 600 RPM and the tangential forces exerted by B on A. Okay. So, what kind of problem is this, right? First question that we need to ask ourselves when we're doing this. What are the key words that we need to pull out of here? What kind of problem do you guys think this is, right? You've got three choices. You've got Newton's law, you've got work energy, you've got impulse momentum. What do we think we're doing here? We're taking hammer, screwdriver, or pliers out of the toolbox. What are we doing? It is. It's momentum, right? Why'd you pick that? Right. Because remember, I said at the beginning of class, you need to find the amount of time that it takes for something to occur, and you're given a moment or a force, you should be automatically thinking impulse momentum, right? So we need the time it takes to reach a certain angular velocity and the magnitude of this force, right? And look, we're given, just like before, we're given the mass of each of the gears and the radii of gyration of each of the gears, right? So we can do some things. So let's start with our diagram, right? Since we've decided on impulse momentum, we'll draw an impulse momentum diagram. So here is, I'm going to draw one just for gear A to start. That looks great. Try that one more time. That's better. This is my pin. This is A. Now, this gear, is this gear in pure rotation, pure translation, or general plane motion? How is this gear going to move? Is it going to translate at all, or is it just going to rotate? Hopefully, it's just going to rotate, right? Because gears, right? Because gears. So we know that originally we'll have some I sub A omega, call it A1, right? So I've got some initial angular momentum here. Right? I've got some initial angular momentum. I can add this to the sum of my rotational impulses, right? Now, I've got reaction forces here and here, but I also have a tangential force here. Remember, because I don't have gear B on this one, right? I split the system, so I have this tangential force. And this tangential force is applied at a distance of the radius of the gear away, which we're also given. And then this will equal the final state where I've got some I sub A omega A. Right, so we got my initial momentum plus all of the forces, right? Plus the free body diagram. Now, is this really the forces, right? I forgot to put a T on this tangential force. Right? I say delta T, but we're going to assume that we start at T equals 0. So any time that we find is going to be the change in time, right? So hey, look, I've got this going. So we got the initial momentum, we got the sum of all my moments on the system that I can create from the forces. And we got this, right? We got the final momentum. What happened to that moment that they gave us, 6 Newton meters? Well, that was applied to gear B, not to gear A, right? So we're not going to talk about that right now. Okay. So looking at this, right? We know we don't have any linear momentum, so we're talking just about angular. We can say, I'll call it point A. I mean, it's the center of this, right? But it's point A. So the angular momentum is equal to the sum of the moments at A times delta T. And that's equal to the final momentum. Well, the angular momentum to start with was IA omega A1. But I'm pretty sure we said that we started at 0, right? It starts from rest. We want to know how long this takes to go from rest to 600 RPM. So we get 0 plus my tangential force times, sorry, I got to create the moment, right? My tangential force creates a moment here. I'm pushing on the edge. It's going to cause a negative rotation, right? A negative moment. What distance is it away? It's RA away. So this is actually minus FT R sub A times delta T. And this is going to equal negative IA omega 2. Everybody following so far? All right. Do you have any questions? All I did was I took the force and I converted it into a moment by multiplying by the distance that we are applying away from the axis of rotation or the point of interest. We know all these things. Well, not all. Right? We don't know F of T. We don't know F of T. And we don't know time. But we know everything else. So we can plug that in, right? So I'll end up with F sub T times delta T times 0.25 equal to 0.400 times 25.1, or you could rewrite that as 40.2. And I'm going to take that as my first equation. I'm going to leave it. And then I'm going to switch over to gear B. Because this is in pure rotation, we only get one equation for each of the bodies, right? Because this is in pure rotation, we only get one equation for each body. So now we're going to hopefully get an equation for part B, right? For gear B, that is a function of that tangential force and the time. And hopefully. So let's draw a diagram for B, right? So we got that equation. We'll draw a diagram for B, right? So the diagram for B, I've got B. I've got some I sub b times omega b1. This is also going to be 0 because everything starts from rest. I've got F tangential. I guess I drew that in the wrong spot. Right? Should be over here. F tangential times T, BYT, and BXT. Because I have reactions from those pins. And that's going to equal IB omega B2. Where did IB come from? We calculated it the last time we did the problem. I just didn't show how we did it. Right. Look at, watch the video from last class. Look at your notes from last week. Where we used the radius of gyration, k squared times m. So we can write our equation here. Right? We know that my initial momentum is 0. My angular momentum here, oh, I forgot one thing, didn't I? On the I have some moment. I don't know why I said it that way. Some moment, not a moment. That'd be weird. I think I was going to go for momentum, but then I stopped short. I don't know. Either way, we have a moment. What is it? It's 6 Newton meters, right? That was from the problem statement. So that has to go on here as well because that's an applied moment. Consider that the torque that we need to start this thing, right? We're applying a constant torque to this gear. How big is it? It's 6 Newton meters. Okay, so what do we have when we sum our moments times delta t? Well, we'll get, remember, we got y, x, and positive this way, right? So we've got m minus f sub t times delta t. I'm sorry, it's not f sub t, right? It's f sub t rb times delta t is equal to IB omega B. Where did this come from? Well, I skipped a step. It's really plus m times, I'll call it delta t since we put it up there. M times delta t minus f tangential times RB delta t, right? I just did the algebra and combined my like terms. And something interesting happens here too, right? Because I know everything except f of t and delta t. I know everything. So I can plug some things in, right? And this is going to be 6 times 6 minus 0.1 f of t times delta t is equal to 0.0192 of 62.8. What's 62.8? Well, that's 600 RPM converted for me, right? We also found that in the last problem. I took a few liberties since we calculated some values last time. I can solve equations 1 and 2. And doing so solve 1 and 2. And doing so gives me delta t is equal to 0.871 seconds, and the force is equal to 46.2 newtons. Which I'm pretty sure is what we found for the force the last time we did the problem, right? What did we find for the force the last time we did the problem? Last time we did it, we found 45.91 newtons. So pretty close. 0.3 newtons off. Right? So that's pretty. I'd say that's pretty good. Count it as a win. You guys have any questions on this one? Right, so I will say this. If you draw the diagram, right, if you draw the diagram and you write down the equations, right, which, you'll be given the equations on an equation sheet for the exam. And don't expect you guys to memorize stuff. But if you draw the diagram, right, you just like a free body and kinetic diagram, you can pull the stuff off of here, right? Directly. Sum all of your momentum, right? Sum all of your linear momentum. Sum all of your angular momentum, right? The second part is all of your impulses, right? So if you had, we'll do another one we'll do another problem that's a little bit more complex, right? This was a pure rotation, which is fine, and it works here, right? But we just don't have any linear momentum. So what happens? What happens if we end up with some linear momentum as well? Like this is pretty similar to the problem we talked about at the beginning of class, right? It's pretty similar, except that we're playing for real now because we're using a bullet. So you'll see that there's a lot of problems with impulse and momentum that are like bullet and block. There's one in your book that is pretty fun. It's the bullet into a block, but the block is a pendulum that's attached to a minecart, which is, I know, it's a super realistic system that you encounter every day, right? For sure. It's not something that's like out of Donkey Kong 64 at all. But here we are talking about it. But that's an interesting problem because you have to chain a lot of things together, right? You've got to do impulse and momentum and work energy, right, to figure things out. But anyway, I've got a projectile weighing 0.08 pounds. And I fire it with a horizontal velocity of 500 feet per second into the lower end of a slender 15-pound bar of length L equals 30 inches. Given that H is 12 inches, so and that the bar is initially at rest, determine the angular velocity of the bar when it reaches the horizontal position, right? So this will get hit and eventually will end up in the horizontal position. Right, so we want the angular velocity when that happens. Okay. So we know a few things right off the bat that they tell us, right? So, all right, before we even get that far, what kind of problem is this? What are we pulling out of the toolbox for this? Newton's law, work energy, or impulse momentum? What do we think? What are the things we should key off of? What are we being asked to find? Let's start with that. What are we being asked to find? Angular velocity. If you're asked to find velocity, right, that's one of those keywords. What method should we be trying to use? Momentum. Also, that's the whole top point of today's lecture, right? So, I mean, context. But yeah, if you're asked for a velocity, more often than not, doing momentum, right? Also, this is a collision problem, really, at its heart, right? The bullet is going to collide with this bar, right? And so because it's a collision problem, we're going to go right to impulse momentum. All right. So how do we do it? Well, since it's impulse momentum, we draw our diagram, right? So let's start there. In state one, right, I've got something, I know, it's uncanny. It's an uncanny representation, right? So that's point G. This is point C. A is at the top. B is at the bottom. I'm going to call the center of gravity G, right? The entire bar has some length L. This distance here, this is H. And the distance from here to here is L over 2. Mercy. No. No. You guys know that these get posted to YouTube, right? All right. So I've just put the dimensions on here, right? Well, what do I have? I also have this bullet here in state 1, right? And that bullet has an initial momentum of the mass of the projectile, we'll call it M sub P, and we'll times V naught, right? Because we know what that is. We were told what both of those quantities are. But the bar itself is at rest. So this is going to be 0, and M bar, V bar is 0 at the start. Right? Why? Because it starts at rest. Right? Should always coordinate axes. There it is. Okay. Everybody's with me so far, right? This describes. Does anybody think I missed anything? Is everybody okay? Does anybody have any questions about how we came up with the initial momentum of this system, right? We have 2 parts to begin with. We have the projectile and we have the bar. Both of them have separate momentum, but we have to draw it, both of them, for the entire system, right? We can add to this our impulses, right? Remember, the impulse portion is like a free body diagram, right? We've removed this from everything. Well, what do I have? I've got the weight of the bar. Also have the weight of the projectile, right? Which we know. It's really small, but we know it. And this is a pinned connection. So I have reaction forces here, right? I didn't put the T in there, right? We certainly could. We could write all of these as W sub B times T. But we know that when we're taking the impulses, right, we're going to end up multiplying by delta T, because that's in the equation. But if it helps you to remember that it's an impulse, right, you can always put times T in there. WB times T and WP times T. Those are the only forces acting on this, right? And then in the final state, right, we're told that the bar is now horizontal, right? And in its final condition, the projectile is still going to, right? We're not told that it hits and sticks, right? We're just told that everything keeps going, right? So this projectile is going to have the mass of the projectile times the velocity of the projectile at state 2. And the bar is going to have the mass of the bar times the velocity of the bar at state 2. And some I omega 2. So at its second state, right, it's rotating about point C. It's rotating about point C here, which is not point G, but we can talk about that in a minute. Everybody okay with this so far, with the diagram? Do you have any questions?
So does the weight of the ball factor at all?
So, I mean, technically yes, but in the real world, or very little. And honestly, if you run this, if you were to ignore the weight of the bullet altogether compared to the weight of the rest of the system, you would get basically the same answer because it is so small, right? Um, it's more complete to include it, but we talked about this, right? If the weights of the objects are very small in comparison to one another, it is oftentimes that we'll just ignore it, right? Now, it's going so fast that the amount of drop isn't going to be seen in the distance that we're looking at it hitting this, right? But you guys probably know, right? I mean, I'm making an assumption that everybody has had some experience with firearms, but in case you don't, right? If you're trying to do target shots at long ranges, you need to account for elevation because you will see a certain amount of drop over a certain amount of time, right? Because of the weight of the bullet. It's not a lot in some cases, but shooting far enough away, it becomes an issue, right? Um, so there's that. Okay. Any other questions? Okay. So remember the equations that we're looking at, right? Let's write those down. We've got a few equations, right? We've got sum of L in the X, L1 in the X, plus the sum of my forces in the X direction, delta T, is equal to the sum of my linear momentum at state 2 in the X direction. I've got sum of my linear momentum in the Y plus the sum of my Y forces, delta T, is equal to the sum of my linear momentum in the Y at the end. I've got sum of my angular momentum. Now, where do we want to take the angular momentum about, right? Where do we want to take the angular momentum about? Ooh. We're going to do it about point C because that's where it's rotating about. Because remember Dr. D's number one rule, right? We should always take moments about the point that has the most forces at it, right? Moments at C. And if we look at C, well, I've got 3 different forces that are going through there. I can cancel a lot of stuff out. And these are the 3 equations that we're going to use. And we're going to talk about how we can apply all of these, right? Now this, because we're not going about G, remember now we have to use that equation we talked about a little bit earlier for I sub O, right? Where I sub O is just the I of the center of gravity plus M times R squared. And we'll talk about it in a second. So let's start with our linear momentum. All right. We'll start with linear momentum in the X direction. The LX equations or equation. Right, so sum of my momentum in the X direction, that's MP times V naught. I have no other momentum to start with, right? There's no Y direction momentum. Everything is 0 at the start except for this. I'm sorry. Did I? Sorry, I read the wrong part of my notes. We'll start with the angular momentum. We'll start with angular momentum. My bad. H sub C equation. All right, so if I'm looking at the beginning, right, I want the angular momentum about point C. Well, I've got MP, and that is L minus H away from C, right? MP is being applied down at the bottom. I want the distance to C. That distance is the total length minus H, right? Everybody's cool with that? This is going to cause a negative angular momentum, right? So this is negative MP times L, MP V naught times L minus H. if I take, all right, so is everybody okay with that? How I determined angular momentum about point C for the projectile at the beginning, right? The rest of the momentum is 0, so we don't have to worry about it, right? Is everybody okay with that based off of this figure? Maybe, maybe not. Okay. This is where we're starting, right? MP V naught, right? That would cause a clockwise rotation, and so that is a negative momentum times L minus H away from C, right? Great.
The L's and O's are not, is that the length of that momentum?
So this is where it's confusion, right? That capital L is the length of the bar. Why don't we pick a different variable real quick so it's not confusing or less confusing? This is script L. Capital L is going to be momentum. Script L is going to be that distance, that 30 inches, okay? So, right, where's the script L? Right, so that's all my initial momentum. Do I have any impulses here? Do I have any impulses? Well, this goes back to Zach's question, right? The impulse due to this projectile's weight is basically 0. Right, it's 0.08 times whatever time I have, right? And that's typically a small window of time. So it's something small multiplied by something else small, which will inevitably give me something small. So we're going to ignore it. We're going to say that it's negligible in this case, right? If we take the moment at C, well, Cy and Cx pass through C, and so does the weight of the bar. So there are no impulses. We're going to say that there's no angular impulses, and therefore we're going to say that angular momentum is conserved here. And if angular momentum is conserved, then this is equal to my final momentum of the projectile, which is still going to be L minus H away, plus I C omega 2. Now, Dr. D jumped the gun with his figure, and I apologize, because there's something that we need to talk about here in a second, but we're going to run through some of the derivation here, right? Because V sub P is great and all, but we want everything in terms of omega, right? We want everything in terms of omega. But I'm going to go back to my drawing. Go back to my drawing for a second. I have this horizontal, right? And I've skipped quite a bit of stuff that's happened here. So instead of having this horizontal, what if I started this analysis with everything vertical? Right, this is still MPVP. But I'm going to say this is right after impact. And this is right after impact. And so I'm going to say this is right after impact. Now, why would we do this? Right? We're going to split it up. We're going to split it up because we can figure out what the velocity is right before impact and what it is right after impact, right? But if we let it produce any further than that, we're not going to accurately capture what it is in the final position, right, with just momentum. We'll talk about what we're going to do in a second, but let's run through the momentum calculation first. Okay. So we've got this here. I'll call this, well, I'm not going to call this an equation 1 yet. I want to take this v sub p, right, the velocity of the projectile, and I want to put it in terms of the angular velocity of the bar. Right, so I can do that, right? I know v naught, I know L, I know H. Instead of Vp, well, that tangential velocity, right, is just r times omega, right? I'm holding this here and I'm applying some tangential velocity here. This is the same as r times omega, right? We've gone through angular velocity before, right? If you want the tangential velocity of any point on a bar, right, it's just r times omega, right? Any point on a rigid body. It's r times omega. Well, how far am I away? Well, I'm L minus h away, that's r. So this becomes L minus h times omega 2 times L minus h, which makes this squared, plus I c omega 2. What happened, Dr. D, what happened to V sub B? Right, we haven't addressed it, but what happened to V sub B? Well, we're not using I bar, right? We're using IC. So it's going to get incorporated into that, right? When I moved to C from G, it gets incorporated in there. You'll see what I'm talking about in a second. I can take this equation, I'll solve it for omega 2. And I get this. Okay. Now look at that. I know L, I know H, I know V naught, I know MP, but I don't know I sub C. Right? So I need to figure out what I sub C is. And we talked a little bit about how to do this. But we can use parallel axis theorem to get it. We looked at a slide before with I sub O with our potato on it and kind of talked about it, right? So what is I sub C? Right? I sub C is just IG plus M times the distance that you are away, right? The distance between the center of gravity and the new point squared. We know I sub G because this is a cylinder rod and we look it up and it's 1/12 M times L squared, which is 1/12 times 15 over 32.2 times 30 over 12 squared, right? Because I want this in pound-feet second squared. I can take I sub C now, right? Because I know this. I sub C is equal to IG, so 0.2426 plus the mass, right, which was 15 over 32.2 times the distance. Well, the distance is L divided by 2 minus H divided by 12, right? Because I want it in feet, and that distance is going to be squared, right? And I know what L and H are, right? So I can plug those in, and if you do that, you get 0.2717 pound-feet second squared. So now I know I sub C, and I know everything in that omega 2 equation. Right? I know everything in the omega 2 equation. So I can solve directly for omega 2, right? I can plug in my numbers and solve for it. So that's what we're going to do. So omega 2 is equal to 0.08 over 32.2 times 500 times 30 over 12 minus 1. You can go back and look at some of this in a second. Excuse me, 6.72 radians per second. And now I know the velocity just after impact of the bullet. Right, so we're halfway, basically. We're basically halfway done because we still need to figure out what happens after this, right? And turns out that this wasn't a straight impulse momentum problem at all. This was an impulse momentum problem that led directly into a work energy problem. So remember, with impulse momentum, you can find out what happened right after impact, but if any amount of time happens after that, your calculations are no bueno anymore, right? So you need some way of figuring out what happened in the time after the impact. And that's where work and energy comes into play, all right? But before we start the work energy part of this, is everybody okay with what we've done so far? Do we have any questions?
How was that L less than 30 over 12?
Why is L 30 over 12? Because it's in feet now instead of inches. So, you can leave it in inches, but then you also need to calculate I in inch pound second squared or pound inch second squared. So it doesn't really matter. One of them, 6 of one, half dozen of the other. Right? Any other questions? Anybody? Doing all right? Okay. So like I said, now we know right after impulse. So now we can, right after the impact, we know how fast this bar is moving, right? And that's great because now we can use our energy equations, right? So let me draw this, right? At the start of state 2, right, which we called state 2 from the last part of the problem, right? I had this bar and this bullet, right? And this distance is L over 2. The total distance being L, and there's some pin here that we're going to call this distance here from here to here H. And I'm actually going to set this up as my D. Right, I'm going to measure everything from that pin C. Okay. And at its final state, which we'll call state 3, I'll have something that looks like this with the center of gravity roughly here. The pin connection will be there, right? So all in line. This distance from here to here, H, L over 2. And that sounds good. Hopefully whatever they're doing, they can get it figured out over the long weekend. Okay. Maybe there's tiny robots in the vents doing cleaning right now. Who knows? All right. So this is so what's the thought process here, right? We can use what we know right before collision to find out what happens right after collision, right? Great. We do that. We find out what happens after collision. After collision, we need to figure out how fast this is going once it gets horizontal. How do we do that? We can use work and energy, right? Because as this goes up, we're going to convert some of this kinetic energy into potential energy and vice versa, right? Depending on how we structure this. Right? So this is the equation that we're looking at, right? And I'm going to claim that it's conservation of energy, right? Because we weren't told that there's any non-conservative forces in there. It's really loud, like really loud. No. Yeah, it's true. I know that they've been messing around with them recently because the faculty offices have been stuck at like 61 degrees the last 2 weeks. Dr. Wright's been in full sweatsuit gear for like 2 weeks. All right, we press on. All right, so we're gonna use conservation of energy. Why? Because we weren't told that there's anything happening like friction or anything in the problem statement, right? And so if you're not told about it, just assume that it's negligible, right? So we're gonna run under the MO of, if you're not told about friction, assume that there is no friction. Assume that you're going to be told when friction needs to be applied. Okay. Well, hey, look at this. The way that I've drawn this, I got rid of all of my potential energy at state 2, right? Because now everything's in line with the datum. So I have potential energy to start with. I have some original kinetic energy. Okay. So when we're looking at this, right, I don't even really need to draw the bullet here because I'm only concerned about the bar. I'm only concerned about the bar. So in state 1, my kinetic energy is going to be 1/2 I sub c omega 2 squared. Right? I know all those things. That's 1/2 times 0.2717 times 6.72 squared, which is 6.13 foot-pounds of energy. Why aren't we taking into, remember that VB, the velocity of the bar, the translation of the bar doesn't come into play because we're analyzing this at point C. And point C does not translate, right? It is pinned in place. We only rotate around point C. All of that V sub B is taken into account in how we found what omega was, okay? It doesn't go away, it just gets transformed into that angular velocity because we've shifted our analysis point from the center of gravity to the pin. All right, what about potential energy at state 1? Do we have any springs? Do we have any springs? No. So we don't have any elastic potential energy. We only have gravitational, right? And gravitational potential energy is mass times gravity times height, or, weight of the bar, right? And this is below the datum, right? Because we're below the datum. So this is actually a negative distance times the length minus the height, right? So for potential energy, we're still tracking the center of gravity of the bar, right? We're still going to track the center of gravity of the bar for potential energy. Plus, because we're feeling good, we will also put the weight of the projectile. Sorry, I wrote the wrong L here. This is L over 2 minus H, and this is L minus H. and that's also a negative term. Why are we including the weight of the projectile? To be more complete, right? Technically, at state 2, they're touching, technically. Why doesn't it contribute to omega 2? Well, remember, it did contribute to omega 2, right? That I sub c term takes, that omega 2 takes into account the velocity of the projectile. Okay. So we know all those things. We can plug them in. Turns out, right, if you had neglected WP here, you'd be fine, right? This is going to be super small. But for completeness, we incorporate it for energy, for terms of energy of the whole system. This is equal to negative 15 times 0.25 minus 0.08 times 1.5, which is negative 3.87 foot-pounds of energy, right? So the negative here indicates that we are below the datum, right? We have gravitational potential energy. Think of it in another way, right? It would take 3.87 foot-pounds of energy to lift this, right? It takes 3.87 foot-pounds of energy to lift it. All right, now that we've got that, we can talk about the kinetic energy at state 2, right? The kinetic energy at state 2 is what? We've got two components, right? Or do we? Are we talking about I sub c or I sub g, right? That's the thing. Now, in the general case, yes, this is I sub g omega 3 and v sub g, right? But remember, everything that we've done so far is in terms of I sub c because that's where we're rotating about. And the velocity at point C is 0 because it doesn't translate. It's a pure rotation about that point. So we're going to continue with this, right? We're going to say, well, this is just 1/2 I sub c omega 3 squared, which is 0.5 times 0.2717 times omega 3 squared. And now, right now, I just plug everything into this equation here, right? So we'll use the next slide to show it. Remember, we had T1 plus V1 is equal to T2, which gives me 6.13 minus 3.87 is equal to 0.5 times 0.2717 times omega 3 squared. So I solve this for omega 3, we get 4.08 radians per second. Okay. Okay, so. Is this a common thing? Will momentum typically transfer into energy? And the answer is yes. Yes, it will. Specifically in the real world as well. If you ever talk about accident reconstruction, this is how you talk about accident reconstruction. You use momentum and energy equations, right? It's basically everything in accident reconstruction. You can figure out the momentum. That gives you the velocity before and after impact. And then energy takes you the rest of the way, right? It gets more complicated when you start having to talk about friction and things, right? But most of the problems we'll see are going to chain momentum into conservation of energy most of the time. That's what we're going to see. You guys have any questions on this one? No, not really. Yes. Up here. So I sub G is something we pull from a table. Good question. I'm pretty sure this is chapter, I want to say 17. I want to say 17. Any other questions? You guys doing okay? All right. Let me do this one today. Hold on. Let me think about something. I do like this problem. I think we will open up class with this problem when we get back. This is a really good problem. Like really good. But I want to talk about impacts today. All right. All right, so we'll do this problem on Wednesday next week. I will double check and make sure that you guys' groups are in too. But if you have a group and you want to come claim this at the end of class, you can. We're not done yet, but we're close. We're getting close. Okay. All right, so no, that was the wrong button. No, thank you. No, thank you. Okay. Whoa. Hey, man. Not cool. The technology. All right. So let's talk about impacts. Let's talk about impacts. If we talk about impacts today, this is going to open up a little bit more time for us to do some problems next week before we start the next topic directly. And since we only have 3 weeks left when we get back from break, we got to make sure that we hit some of the topics, especially since 2 weeks from this Friday, we're going to do our final exam, right? If everything goes according to plan. We do have some slop in there, so we could move it around if we need to. But anyway, eccentric impacts. We talked about impacts, right? We talked about impacts. What is an eccentric impact? Well, an eccentric impact is one that happens off center, right? It's one that's like an oblique impact. It's not the centers of gravity are not lined up and they're not hitting on the direct line, right? Like we have here. And we can talk about these in two distinct points, right? We have the period of deformation, right? And so we watched the video with the golf ball, right? And we had the golf swing, and when you hit the golf ball, you have this period of deformation where the golf ball is physically changing because it's been hit so hard, right? And then we have the period of restitution, which happens directly afterwards, which is when the ball expands back to its normal size, right? And all of that energy is getting loaded up through the deformation like a spring, and then it's being released, right? And that's where the shot speed comes from, right? So the principle of impulse and momentum is often supplemented by the coefficient of restitution, right? Which is given by this equation, right? These velocities are for the points of impact. So where these two things collided, that's the point of impact, right? Where we have the final velocity of body B in the normal direction, minus the final velocity of body A in the normal direction divided by the initial velocity of body A normal minus the initial velocity of body B. Okay. This is the equation. That'll be on your equation sheet, right? So let's see what we know already just conceptually about Logan. So yes, absolutely.
Is there a definition for
No, I didn't give one. They're impacts that don't happen through the center of gravity. Right, so you see that these two things are like, they're shaped like beans, right? Call them beans. The potato is the bean, right? These two beans, I think that's pretty clear that that impact is not traveling through the center of gravity of the bean, right? But it's traveling along this line N, right? This line N. And so we want all the velocity along the line N, right? That's going to be the direction the impact travels. Logan.
what's the
Yeah. Okay. So when we talk about those integrals, which we're not going to really have to calculate, remember how we calculate impulse and momentum, right? Impulse momentum equation tells us that the sum of my initial momentum plus the sum of all of my impulses is equal to my sum of my final momentum, right? That integral r dt and that integral p dt tracks how much force happens during deformation and tracks it as an impulse, and the restitution period tracks how much force is being produced by the expansion again. So it's kind of like in this, the simplest way you can think about it is it's like a spring, right? You've got this spring, you squeeze it, how much force did you have to squeeze it by that much, and then how much force was given off by letting it go. Okay. Any other questions so far? Let's see what we know, gut feelings about impact. I think we'll know a little bit more than we think we know. All right. So these two cars hit each other at point P, right? So this is an eccentric impact, right? Because it's offset from the center of gravity, all right? Which of the following can you use to help you analyze this collision? Linear momentum of car A is conserved. A. B. Linear momentum of the combined two cars is conserved. C. The total kinetic energy before impact equals the total kinetic energy after impact. And D. The angular momentum about the CG of car B is conserved. So what do you guys think? Do you think A, that the linear momentum of car A is conserved? Show of hands. Who thinks A is true? Who thinks B, the linear momentum of the combined two cars is conserved? This is B. So another way of saying this is the total linear momentum of the system is conserved. Okay. C, the total kinetic energy before the impact equals the total kinetic energy after. Thinks it's C. Okay. And D, the angular momentum about the CG of car B is conserved. Remember what that means, right? That the sum of the moments about the center of gravity would be 0. Who thinks it's D? Okay, so most had some B's and some C's, right? It's B. Why is it B? Well, first of all, it's not C, right? And why is it not C, right? It's not C because this impact is going to cause energy to be created via heat and sound. Right? So the mechanical energy is not conserved here. There's losses. Right? The two cars hitting each other causes a tremendous amount of sound, right? And deformation of the metal, and that takes energy to do. B is the correct answer. Why? Because if you were to draw the impulse momentum diagram here, right, the impulses of the car hitting are going to cancel, right? If they touch at point P, right, the force exerted on car A by car B is equal and opposite to the force exerted by car A on car B, right? So the linear momentum of the entire system is conserved in this case. Let's watch this video.
In this video, we're going to focus on problems that relate to inelastic collisions. In an inelastic collision, what you need to know is that momentum is conserved, but kinetic energy is not conserved. So anytime you have two objects that stick together, typically it's usually an inelastic collision. Like this problem. So we have a block moving east at 15 meters per second, and it collides with a 5 kilogram block at rest. The two blocks stick together. What is the final speed of the two blocks? So whenever you have objects sticking together, it's an inelastic collision. But for all types of collisions, momentum is going to be conserved. If it's an inelastic or elastic collision, doesn't matter. So for any collision, we could use this equation. The total momentum before is equal to the momentum after the collision. Now let's draw a picture. So we have a 10 kilogram block moving east. And this block is going to strike another block. This one's going to be a 5 kilogram block, and it's currently at rest. Now after the two collide, these two blocks will be sticking together. Our goal is to calculate the final speed of these two blocks. Because they stick together, they're going to move together at the same final speed. So now let's focus on the equation. Before the collision, we have two blocks. Let's call the 10 kilogram block block 1. So it has a momentum of m1 times v1. Momentum is mass times velocity. And then we need to add the momentum of block 2. So that's the total momentum before the collision, and that should equal the total momentum after the collision. Now the mass is not going to change, but the speed is going to change. So v1 prime represents the final speed of block 1, which is the 10 kilogram mass. And v2 final, or v2 prime, that's the final speed of block 2. Now because these two stick together, v1 prime and v2 prime, they're the same. So we could just call it v, or just v final. So we could use the same symbol to represent those two velocities because they're identical. So on the right side, what I'm going to do is factor out v final. So this is the equation that you should use whenever you have an inelastic collision, and when two objects they stick together, they're going to have the same final speed. So let's plug in the values that we know. So the mass of the first block is 10, and it's moving at a speed of 15 meters per second. Now the second block is at rest, so it has no momentum because the speed is 0. And that's going to equal the final speed times the sum of the two masses, which is 10 plus 5. Now 10 times 15 is 150, and 10 plus 5 is 15. So v final is going to be 150 divided by 15, which is 10. So it's 10 meters per second. So here we had a 10 kilogram mass moving at a speed of 15 meters per second. And now we have a mass of 15 kilograms moving at a speed of 10 meters per second. Whenever momentum is conserved, if you increase the mass of the system, the speed decreases. So the mass of the system went from 10 to 15, and the speed decreased from 15 to 10. Make sure you understand that concept. Now let's move on to our second problem. You could try it if you want to. A 15-gram bullet is fired horizontally at a speed of 350 meters per second into a 1.2 kilogram block that hangs by a vertical string as shown below. So this is the 15-gram bullet, and it's moving at a speed of 350 meters per second. Now once it strikes the block, the bullet remains embedded in the block. So the block is going to rise. So we're going to have the bullet inside the block. And we need to find the final speed of the bullet in the block. So after the collision, we need to know how fast these two are moving as a whole. And also, part B, how high the bullet and the block will rise. So we need to calculate the height difference between the center of mass between the bullet mass system after the collision and before the collision. So how can we do that? Well, let's focus on part A. So we have two objects sticking together. Once the bullet is inside the block, they're sticking together. So we can use the same formula that we did, or that we used in the last problem, which is m1v1 plus m2v2, and that's equal to m1 plus m2 times the final speed. So let's calculate the final speed. The mass of the bullet is 15 grams, but we need that in kilograms, so we got to divide it by 1,000. So m1 is going to be 0.015 kilograms. The speed is 350 meters per second. Now the block is initially at rest, it's just hanging still. m1 plus m2, that's going to be 0.015 plus 1.2. And now let's calculate the final speed. So first let's multiply 0.015 by 350. And so you should get 5.25. And then let's add 0.015 plus 1.2. So that's 1.215. Now to calculate the final speed, it's going to be 5.25 divided by 1.215. And so you should get a final speed of 4.321 meters per second. Now that we have the final speed, how can we use that to calculate how high the bullet block system will rise? We can use conservation of energy, but you need to be careful because this is an inelastic collision, and during the collision, kinetic energy was lost. However, once the collision's over, once the bullet is inside the block, the energy that it has after the collision will be conserved as it moves up. So during the collision, kinetic energy is not conserved if it's an inelastic collision when two objects stick together. But after the collision, after energy has been lost, as the system moves up, energy will be conserved. So the kinetic energy of the bullet block system will be converted to potential energy as it moves to a higher position. So I'm going to set Ke equal to Pe. Kinetic energy is 1/2 mv squared, and the potential energy is mgh. So the mass is not going to change, so we could cancel m. And now let's solve for h. So we have 1/2 v squared, which is 4.321, and that's equal to gh, or 9.8 times h. So 4.321 squared times 0.5, that's 9.3355. And then we need to take that number divided by 9.8. And so this will give you a height of 0.9526 meters. So that's how high the bullet block system will rise above its initial level. Now let's work on the last question in this video. So a 25-gram bullet is fired horizontally at a speed of 400 meters per second into a 1.5 kilogram block that rests on a horizontal surface. So let's draw a picture. So here's the 1.5 kilogram block. And here is the bullet that's flying towards it. Now the bullet emerges from the block at a speed of 150 meters per second. So we still have the same block, but the bullet leaves the block. So some of the momentum from the bullet is transferred to the block, causing the block to move. Our goal is to calculate the final speed of that block. So the initial speed of the bullet is 400 meters per second, and the final speed is 150 meters per second. So you can see it lost momentum. And so the bullet exerted a force on the block, causing the block to accelerate. And the block exerted an equal amount of force on the bullet, causing the bullet to decelerate from a speed of 400 to 150. So these two objects, whenever they collide, or whenever any two objects collide, they exert forces on each other. So one object will accelerate, it's going to speed up, and the other object will slow down. But now let's go ahead and calculate the final speed of the block. So the initial momentum is going to equal the final momentum. So m1v1 plus m2v2 will equal m1v1 prime plus m2v2 prime. So we can't just have one final speed like we did in the last two problems, because the speed of the block and the speed of the bullet, they're not the same in this problem. They don't stick together. However, if kinetic energy is not conserved, this will still be an inelastic collision. But we don't need to worry about that, because this equation alone is enough to find what we're looking for. So the mass of the bullet, 25 grams, is equivalent to 0.025 kilograms if you divide it by 1,000. The initial speed of the bullet is 400. Now m2v2, that's the momentum of the block, which is initially at rest. Now, after the collision, the block is moving. So we're looking for v1 prime. We're going to say that's the final velocity of the block. The bullet still has the same mass, but the new speed of the bullet is 150. So we got to solve for v. So first, let's multiply 0.025 by 400. So that is equal to 10. And then 0.025 times 150 is 3.75. Now let's subtract both sides by 3.75. So 10 minus 3.75 is 6.25. And then to find the final speed of block 1, or just the block in general, it's going to be 6.25 divided by 1.5. And so that's 4.167 meters per second. So that's how you can calculate the final speed of the block.
All right. So those were all linear momentum problems, right? We haven't had to do anything. Now the first one, you probably could have used angular momentum, right? You also said something at the beginning of the video. Also said something at the beginning of the video, right? That momentum is always conserved. We already went over that it's not necessarily conserved, right? So it depends on external conditions. We're not going to do this right now. I don't think we have enough time, and it's day before Thanksgiving, so let's let you out a little early. It's not a big deal. I'll go and check the check LoudCloud, make sure. I don't know why it's not updating me when I get PMs, but I'll check on the CLC groups. One person from each CLC group, though, needs to claim one of these so that you can have it and you can start measuring stuff. and Julian. I don't know. Last week he was. I don't know if this week he is. If not, we can redistribute some people to get a couple groups of 4 because it's not fair to do a CLC with 2. But more on that later. All right, so that's your central shaft. When you do your 3D printing stuff, make sure that that is what you're using as, what you're connecting to. Okay. Yeah, friends and blades. Typical methods of getting things on are press fitting and hot glue. It's very scientific. I know it's very technical. That's typically what students have done in the past, and it works just fine. We're not allowed to technically use super glue because then the 3D prints cannot be recycled, because apparently super glue gives off toxic fumes or whatever. But yeah, so there's that. We'll talk more about connecting and building stuff though. Like if you wanted to use something else, that's fine. Unfortunately, outside of 3D printing, there's no budget for this class to get you guys anything outside of 3D print stuff and hot glue. So that's kind of where we're at. All right. That's gonna be it for today, guys. That's gonna be it. So yeah, I have to get you guys the I have to get you that document. It's on my list. I'll post it today. If you need measurements, we're gonna try to use the wind tunnel. I don't know if it's up and running, and I actually don't even know where it is right now. So I can't even tell you to go take measurements of it. So I'll ask Dr. Williams what the thing is. And by thing, I mean what the size of the test section is. All right.